Theoretical physics is a branch of physics which employs mathematical models and abstractions of physical objects and systems to rationalize, explain and predict natural phenomena. This is in contrast to experimental physics, which uses experimental tools to probe these phenomena. The advancement of science depends in general on the interplay between experimental studies and theory. In some cases, theoretical physics adheres to standards of mathematical rigor while giving little weight to experiments and observations. For example, while developing special relativity, Albert Einstein was concerned with the Lorentz transformation, which left Maxwell's equations invariant, but was apparently uninterested in the Michelson-Morley experiment on Earth's drift through a luminiferous ether. Conversely, Einstein was awarded the Nobel Prize for explaining the photoelectric effect, previously an experimental result lacking a theoretical formulation. Overview. A physical theory is a model of physical events. It is judged by the extent to which its predictions agree with empirical observations. The quality of a physical theory is also judged on its ability to make new predictions which can be verified by new observations. A physical theory differs from a mathematical theorem in that while both are based on some form of axioms, judgment of mathematical applicability is not based on agreement with any experimental results. A physical theory similarly differs from a mathematical theory, in the sense that the word theory has a different meaning in mathematical terms. A physical theory involves one or more relationships between various measurable quantities. Archimedes realized that a ship floats by displacing its mass of water. Pythagoras understood the relation between the length of a vibrating string and the musical tone it produces. Other examples include entropy as a measure of the uncertainty regarding the positions and motions of unseen particles, and the quantum mechanical idea that energy are not continuously variable. Theoretical physics consists of several different approaches. In this regard, theoretical particle physics forms a good example. For instance, phenomenologists might employ empirical formulas to agree with experimental results, often without deep physical understanding. Modelers often appear much like phenomenologists, but try to model speculative theories that have certain desirable features, or apply the techniques of mathematical modeling to physics problems. Some attempt to create approximate theories, called effective theories, because fully developed theories may be regarded as unsolvable or too complicated. Other theorists may try to unify, formalize, reinterpret or generalize extant theories, or create completely new ones altogether. Sometimes the vision provided by pure mathematical systems can provide clues to how a physical system might be modeled, e.g., the notion, due to Riemann and others, that space itself might be curved. Theoretical problems that need computational investigation are often the concern of computational physics. Theoretical advances may consist in setting aside old, incorrect paradigms, or maybe an alternative model that provides answers that are more accurate or that can be more widely applied. In the latter case, a correspondence principle will be required to recover the previously known result. Sometimes, though, advances may proceed along different paths. For example, an essentially correct theory may need some conceptual or factual revisions. Atomic theory, first postulated millennia ago, and the two-fluid theory of electricity are two cases in this point. However, an exception to all the above is the wave-particle duality, a theory combining aspects of different, opposing models via the Bohr complementarity principle. Physical theories become accepted if they are able to make correct predictions and no incorrect ones. The theory should have, at least as a secondary objective, a certain economy and elegance. A notion, sometimes called Occam's razor, after the 13th century English philosopher William of Ockham, in which the simpler of two theories that describe the same matter just as adequately is preferred. They are also more likely to be accepted if they connect a wide range of phenomena. Testing the consequences of a theory is part of the scientific method. Physical theories can be grouped into three categories: mainstream theories, proposed theories, and fringe theories. History. Theoretical physics began at least 2,300 years ago, under the pre-Socratic philosophy, and continued by Plato and Aristotle, whose views held sway for a millennium. During the rise of medieval universities, the only acknowledged intellectual disciplines were the 7 liberal arts of the trivium like grammar, logic, and rhetoric, and of the quadrivium like arithmetic, geometry, music, and astronomy. During the Middle Ages and Renaissance, the concept of experimental science, the counterpoint to theory, began with scholars such as Ibn el-Haytham and Francis Bacon. As the scientific revolution gathered pace, the concepts of matter, energy, space, time, and causality slowly began to acquire the form we know today, and other sciences spun off from the rubric of natural philosophy. Thus began the modern era of theory with the Copernican paradigm shift in astronomy, soon followed by Johannes Kepler's expressions for planetary orbits, which summarized the meticulous observations of Tycho Brahe. The works of these men can perhaps be considered to constitute the scientific revolution. The great push toward the modern concept of explanation started with Galileo, one of the few physicists who was both a consummate theoretician and a great experimentalist. The analytic geometry and mechanics of Descartes were incorporated into the calculus and mechanics of Isaac Newton, another theoretician, experimentalist of the highest order, writing Principia Mathematica. In it contained a grand synthesis of the work of Copernicus, Galileo, and Kepler, as well as Newton's theories of mechanics and gravitation, which held sway as worldviews until the early 20th century. Simultaneously, progress was also made in optics, courtesy of Newton, Descartes, and the Dutchmen Snell and Huygens. In the 18th and 19th centuries, Joseph Louis Lagrange, Leonhard Euler, and William Rowan Hamilton would extend the theory of classical mechanics considerably. They picked up the interactive intertwining of mathematics and physics begun 2 millennia earlier by Pythagoras. Among the great conceptual achievements of the 19th and 20th centuries were the consolidation of the idea of energy by the inclusion of heat, electricity, and magnetism, and then light, the laws of thermodynamics, and most importantly the introduction of the singular concept of entropy began to provide a macroscopic explanation for the properties of matter. Statistical mechanics emerged as an offshoot of thermodynamics late in the 19th century. Another important event in the 19th century was the discovery of electromagnetic theory, unifying the previously separate phenomena of electricity, magnetism, and light, the pillars of modern physics. And perhaps the most revolutionary theories in the history of physics have been relativity theory and quantum mechanics. Newtonian mechanics was subsumed under special relativity, and Newton's gravity was given a kinematic explanation by general relativity. Quantum mechanics led to an understanding of blackbody radiation and of anomalies in the specific heats of solids, and finally to an understanding of the internal structures of atoms and molecules. Quantum mechanics soon gave way to the formulation of quantum field theory, begun in the late 1920s. In the aftermath of World War II, more progress brought much renewed interest in QFD, which had since the early efforts stagnated. The same period also saw fresh attacks on the problems of superconductivity and phase transitions, as well as the first applications of QFT in the area of theoretical condensed matter. The 1960s and 70s saw the formulation of the standard model of particle physics using QFT and progress in condensed matter physics, in parallel to the applications of relativity to problems in astronomy and cosmology respectively. All of these achievements depended on the theoretical physics as a moving force, both to suggest experiments and to consolidate results, often by ingenious application of existing mathematics, or, as in the case of Descartes and Newton, by inventing new mathematics. Fourier's studies of heat conduction led to a new branch of mathematics, infinite, orthogonal series. Modern theoretical physics attempts to unify theories and explain phenomena in further attempts to understand the universe, from the cosmological to the elementary particle scale. Where experimentation cannot be done, theoretical physics still tries to advance through the use of mathematical models. Mainstream theories. Mainstream theories are the body of knowledge of both factual and scientific views and possess a usual scientific quality of the tests of repeatability, consistency with existing well-established science and experimentation. There do exist mainstream theories that are generally accepted theories based solely upon their effects explaining a wide variety of data, although the detection, explanation, and possible composition are subjects of debate. Examples: black hole thermodynamics, classical mechanics, condensed matter physics, conservation of energy, dark matter, dynamics, electromagnetism, field theory, fluid dynamics, general relativity, particle physics, physical cosmology, quantum chromodynamics, quantum computers, quantum electrochemistry, quantum electrodynamics, quantum field theory, quantum information theory, quantum mechanics, quantum gravity, solid mechanics, special relativity, standard model, statistical mechanics, thermodynamics. Proposed theories. The proposed theories of physics are usually relatively new theories which deal with the study of physics, which include scientific approaches, means for determining the validity of models, and new types of reasoning used to arrive at the theory. However, some proposed theories include theories that have been around for decades and have eluded methods of discovery and testing. Proposed theories can include fringe theories in the process of becoming established. Proposed theories usually have not been tested. Examples: causal sets, dark energy or Einstein's cosmological constant, Einstein-Rosen bridge, emergence, grand unification theory, loop quantum gravity, M-theory, scale relativity, string theory, supersymmetry, theory of everything, and particle physics. Fringe theories. Fringe theories include any new area of scientific endeavor in the process of becoming established, and some proposed theories. It can include speculative sciences. This includes physics fields and physical theories presented in accordance with known evidence, and a body of associated predictions have been made according to that theory. Some fringe theories go on to become a widely accepted part of physics. Other fringe theories end up being disproven. Some fringe theories are a form of proto-science and others are a form of pseudoscience. The falsification of the original theory sometimes leads to reformulation of the theory. Examples: electrogravitics, Tesla's dynamic theory of gravity, luminiferous ether, orgone. Thought experiments versus real experiments. Thought experiments are situations created in one's mind, asking a question akin to, suppose you are in this situation, assuming such is true, what would follow? They are usually created to investigate phenomena that are not readily experienced in everyday situations. Famous examples of such thought experiments are Schrödinger's cat, the EPR thought experiment, simple illustrations of time dilation, and so on. These usually lead to real experiments designed to verify that the conclusion of the thought experiments are correct. The EPR thought experiment led to the Bell inequalities, which were then tested to various degrees of rigor, leading to the acceptance of the current formulation of quantum mechanics and probabilism as a working hypothesis. Suggested reading list. Physical Sciences. Encyclopædia Britannica 25. 1994. Duhem, Pierre. La théorie physique, son objet, sa structure. 2nd edition 1914. English translation. The Physical Theory, Its Purpose, Its Structure. Republished by Joseph Vrin Philosophical Bookstore, ISBN 2711602214. Feynman, A. Al. The Feynman Lectures on Physics. First edition. Addison Wesley. Best-selling 3-volume textbook covering the span of physics. Reference for both graduate student and professional researcher alike. Landau et al. Course of Theoretical Physics. Famous series of books dealing with theoretical concepts in physics covering 10 volumes. Translated into many languages and reprinted over many editions. Often known simply as Landau and Lifshitz, or Landau-Lifshitz, in the literature. Longueur, Theoretical Concepts in Physics. An alternative view of theoretical reasoning in physics. Cambridge University Press, 2D edition. ISBN 0521528788X. ISBN 9780521528788. Planck, Max. 8 Lectures on Theoretical Physics. Library of Alexandria. ISBN 1465521887. ISBN 9781465521880. A set of lectures given in 1909 at Columbia University. Sommerfeld, Arnold. Vorlesungen über theoretische Physik, German. 6 volumes. A series of lessons from a master educator of theoretical physicists.